Hey y'all, today we're going to introduce a new concept which is called interparticle forces. We've spent a lot of time this year talking about forces within molecules, bonds. But today what we're going to do is we're going to explore what happens when we have different molecules present near each other and how those molecules themselves will interact. Now we've kind of touched on this back in gas laws because one of the assumptions for ideal gas laws was that molecules don't interact. Today, we're going to learn about how molecules do interact, and we're going to explore the basics of the different interparticle forces that we're going to see this year in chemistry. Interparticle forces are going to be based on Coulomb's law. Remember, Coulomb's law is charge over distance, effectively. And in interparticle forces, we're looking at molecules which might or might not have any real charges. But we've already talked about how we can identify whether a particle or a molecule is polar or nonpolar. Well, polarity might not give you a full charge, but it does give you a partial charge. These are the dipole moments, which we have spoken about already. Nonpolar molecules, meanwhile, they don't have partial charges that are permanent, but we're going to talk today about how they do have temporary dipoles which can be induced and can exist. Let's go ahead and start by defining a few of these different interparticle forces. If you think about a fish tank, the odds that fish are going to be evenly distributed throughout the entirety of the fish tank at any given moment is pretty small. More often than not, there are going to be more fish on one side than on another. In a molecule, the electrons behave in much the same way. In many cases, the electrons are going to be distributed unevenly, even if it's a nonpolar molecule. And that's just because molecules have electron clouds. And in the electron cloud, electrons are moving constantly. So the odds that you're going to have the exact same number of electrons evenly distributed across the entirety of the molecule is pretty small. It gets even smaller as the number of electrons gets bigger. So if you think about our fish tank, if you have two fish, there's a decent chance that you're going to have one fish on either side of the tank. But if you have 100 fish, now the odds that you're going to have 50 on one side and 50 on the other, well, that's getting much, much smaller. In a molecule, the more electrons you have, the less likely they are to be evenly distributed. But that's also not going to be permanent. One side that had more electrons in one moment might all of a sudden switch, and now it's the other side with more electrons. This would be called a temporary dipole. A temporary dipole is a dipole. Remember, a dipole is where you have an uneven distribution of electrons. A temporary dipole is one where the electrons are unevenly distributed, but not for a long period of time, just temporary. This creates a force called a London dispersion force. And a London dispersion force is created when these temporary induced dipoles or temporary dipoles are going to interact with each other. So the positive dipole that's temporary on one molecule might very, very briefly interact with a negative temporary dipole on another. London dispersion forces exist in any molecule that has an electron cloud. The bigger the molecule, the more the London dispersion forces play a role. And when I say big, I mean it in two ways. One, size of electron cloud. And when I say size of electron cloud, we can normally use molar mass as a proxy for figuring out how big the electron cloud is going to be. The more the molar mass, the bigger the electron cloud. But it also has to do with how wide the electron cloud is spread. So if we think about a big molecule that's all bundled together in the center, that electron cloud is probably going to be a little bit more evenly distributed. A much longer, skinnier molecule, like a long chain lipid, for example, all of a sudden is going to have a much longer chain of electron clouds. So it's not going to be as bundled together, if you will, or as evenly packed. And so the odds of dipoles existing will increase as the molecule becomes longer. So these temporary dipoles create very, very weak forces of attraction, relatively speaking, but they can add up. We're going to talk about how we compare forces of attraction in a few minutes. The next force that we want to look at are going to be created not by temporary dipoles, but by permanent dipoles. Permanent dipole moments are going to be due to uneven distribution of electrons due to electronegativity differences in a polar molecule. So if we've identified a molecule as polar, it will experience dipole-dipole forces in addition to the London dispersion forces, which we just talked about in the last moment. Permanent dipoles have a slightly stronger charge, relatively speaking. So if we go back to Coulomb's law, the charge over the distance, the charge element is going to be slightly greater, even though they're not full charges. These are just partial charges. These partial charges are sufficient to create a Coulombic force of attraction between molecules. Dipole-dipole forces are going to be a more permanent force of attraction than the temporary dipoles. But again, what you're going to see in dipole moments is not always constant. Some molecules have stronger dipoles than others. Therefore, not all dipole-dipole forces of attraction are going to be equal. Some molecules will show a greater dipole-dipole force if they are a more polar molecule. Others will show a weaker dipole-dipole force of attraction if they are less polar. The way we can determine whether something is more polar or less polar, we just have to look at the electronegativities of the atoms in the molecule itself. Within dipole-dipole forces, there's a subcategory. I just said that dipole-dipole forces get stronger as the electronegativities become more dramatic. Well, the most dramatic electronegativity differences that exist are going to be between fluorine and hydrogen, nitrogen and hydrogen, as well as oxygen and hydrogen. These are extreme differences in electronegativity, which means they create extremely strong dipole moments. These dipole moments are strong enough where they can actually create a subcategory of attractions. We call these hydrogen bond forces. Hydrogen bond forces are a subcategory of dipole-dipole force. So when we look at hydrogen bond forces, we are only going to see hydrogen bond forces between molecules that have hydrogen directly covalently bound to a nitrogen, hydrogen directly covalently bound to a oxygen, or directly covalently bound to a fluorine. All right. One of the things that the mnemonic I use is hydrogen bonding is fun to do, right? It's F-O-N, fun to do. Get it? Not great, but whatever. The idea here is, though, that the hydrogen must be covalently bound to the nitrogen, oxygen, or fluorine in order for there to be a big enough difference in electronegativities. A random hydrogen bound to a carbon isn't going to show a positive enough dipole in order to show that force of attraction. So what we need to see here specifically when we're looking for hydrogen bond forces is going to be a hydrogen covalently bound to a nitrogen, an oxygen, or a fluorine, and that will be attracted to another dipole of another molecule, many times the same one, and you can see that here with the dashed lines. So what experiences the hydrogen bond forces are going to be the negative dipole of one molecule with the positive dipole of the other. The negative dipole is going to be associated with the oxygen, the nitrogen, and the fluorine, and the positive dipole is going to be associated with the hydrogen. That's where the attraction is going to be. Remember, it's a covalent bond between the hydrogen and the nitrogen, oxygen, or fluorine, and then those create a dipole strong enough to show hydrogen bond forces between that molecule and another molecule. Those are the intermolecular forces. Let's talk about interparticle. Now, obviously, if it's Coulomb's law that controls this, then partial charges aren't the only things that exist. We've also talked about full charges in the case of ions. Ion dipole forces of attraction exist. This is where an ion is going to be closely attracted to a dipole based off of that Coulombic force of attraction. A positively charged ion will be attracted to the negative dipole of a molecule, and a negatively charged ion will be attracted to a positive dipole of a molecule. So ion dipole forces do exist, and they are going to be, again, predicated on Coulomb's law, and are going to present themselves in oftentimes as solutions, where we dissolve into a solution, say a salt, sodium chloride. The chlorine ion is going to be most attracted to the hydrogen end of water, and the sodium ion is going to be most attracted to the oxygen end of water. And again, this is because the sodium is a positively charged ion, the oxygen end is the negative dipole. The chlorine ion is negatively charged, but the hydrogen end of the water is a positive dipole. So you see this as an attractive force. This is called an ion dipole force. Ionic bonding is another type of interparticle force, although oftentimes it's a kind of a gray area. We look at ionic bonding in the same way, where it's Coulomb's law that predicates the ionic bonding, where the greater the charge of the ions involved, the stronger the force of attraction. The smaller the ions involved, also the stronger the force of interaction. So when we're looking at ionic bonding, you can also think of it as an interparticle force. One thing I've been careful to do in this video so far is talk about how any of these are stronger or weaker than the others. There's only one way to really determine whether an interparticle force is stronger than another, and that's to look at the evidence. The evidence is always going to be in the form of melting point or boiling point. If the melting point is higher, the interparticle forces are stronger. If the boiling point is higher, the interparticle forces are stronger. So if I look at two molecules, water and butter, water experiences hydrogen bond forces. Now, if we think about Coulomb's law, that seems like that would be a stronger force of attraction than the butter, which only experiences as a lipid interparticle forces of London dispersion forces. But here's the thing. When we look at this, the reality is that butter stays solid at room temperature and water's liquid. Well, that means butter didn't melt at room temperature. That means by the evidence, the London dispersion forces in butter are stronger than the hydrogen bond forces that exist in the water. That's a big deal. So we cannot simply rank the forces of attraction based off of just looking at the names or the interactions. We have to look at the evidence. The melting point or the boiling point will be the evidence that we use in every circumstance to determine the rankings of the different interparticle forces. So that was our introduction to interparticle forces. In the next couple of videos, we're going to expound upon this a little bit and go a little bit deeper into each one, and also some examples of molecules that experience it. I hope you enjoyed this video, and I'll see you in the next one.